Okay, guys, let's have a look at these here. So, for number 1, ionic or molecular?
Ionic.
Ionic. Sodium is a metal. All right, so I write the name of the metal, sodium, and I write the name of the nonmetal, phosphide. Okay, we're good on that one. Number 2, ionic or molecular?
Ionic.
Also ionic. Magnesium is a metal. All right, so write the name of the metal, magnesium. Okay, write the name of the nonmetal, nitrate, because this time the nonmetal is a polyatomic ion. Okay, if you got questions as we go here, guys, don't be afraid to ask, okay? Number 3, ionic or molecular?
Ionic.
Ionic, okay, so we got nickel sulfide. What am I missing? Roman numerals. Nickel has more than one possible charge. Okay, sulfur is a -2. There's one sulfur, there's one nickel. That means the charge on nickel has to be the same so that that compound comes out to 0. So this is nickel 2 sulfide. Okay, for number 4, okay, ionic and molecular. Molecular. Okay, silicone and fluorine are both non-metals. So this is going to be silicone tetrafluoride. Okay. And last one, ionic or molecular? Ionic. Tin is a metal, okay, and it is with a polyatomic ion, okay, sulfate, so we'll have tin sulfate. Sulfate is always a -2, and there are 2 sulfates for a total of 4 negative charges. That means I got to get 4 positive charges from a single tin 4 sulfates. Okay? Would you get it wrong if you forget the Roman numeral?
Yes.
Yes, you would. Okay, you got to have the Roman numeral. And you might have noticed on the first quiz that I don't give half marks. Okay? It's either right or it's wrong. Okay? All right. For number 6. We're on number 6 now. Okay, ionic or molecular? Ionic. Lithium is a metal, carbonate is a polyatomic ion. So write the symbol for the metal with its charge. Write the symbol for the nonmetal. Write its charge. Drop and swap. Li2CO3 or Li2 bracket CO3. Either way is fine. Okay. All right. Ionic or molecular for number 7?
Molecular.
Molecular. We see all those prefixes, right? So disulfur means how many sulfur?
2.
How many oxygens? Good. Hey, number 8, ionic or molecular? Ionic. We only see Roman numerals in ionic compounds. Okay, so we are looking at cobalt with the 2+ charge with oxygen, which happens to be a -2 charge. So CO2O2?
No.
No. Yeah. Coo. Yeah, COO. Okay. If we put an L after that, that'd be really cool. But, yeah. All right, that's lame. Okay, number 9, calcium nitride. Ionic or molecular? All right. See, I can't even say it like you guys. Okay, calcium 2+ and nitride -3. Okay, drop and swap. We got Ca3N2. All right. And last one, tetraphosphorus decasulfide. Molecular. Okay, how many phosphorus?
4.
Okay. How many sulfurs?
10.
All right. Should I reduce that?
No.
No, I should not. Okay, definitely, emphatically no, I should not reduce that because it is molecular and we don't reduce molecular ones. Okay, is that ringing a bell? Is this exactly what I'm going to do on the quiz on Friday?
Probably.
Yeah, actually, I think it is actually 5 of each, okay, on there, and then some solubility and properties questions in addition to that. Okay, that will be what is on Friday's quiz. So, quick review of properties of compounds and things that might be useful in identifying your unknowns from yesterday. I have a crystalline solid that is blue in color and is highly soluble in water and has a fairly neutral pH and conducts electricity in solution. It would probably contain what? It would be ionic, but it would contain copper. Yeah, so it could be like, you know, any copper-containing ionic compound. Okay. I have a unknown substance that is highly acidic. What is probably acting as the metal? Hydrogen, okay? Things like that. Those are the kinds of things that could be questions, okay, on Friday's quiz about properties of compounds. Okay, bases would all have what ion in them? OH. Okay, question for you. Is that a base?
No.
Okay, why not?
There's more hydrogen.
There's what?
More hydrogen.
There is, but actually not why it's not a base. What kind of compound is it?
Molecular.
Right, which means that OH isn't coming off, is it? No. Okay, remember guys, something is only a strong base if it has OH in it and that OH can come off. Okay, that means it has to be ionic. Okay, that's a strong base. Okay, the other one is not. Okay, because if I put this one in water, it dissociates into sodium and hydroxide can then act as a base. Okay, in this one here, okay, which is ethanol, that's a molecular compound. Those things are staying together. It's not going to dissociate when I put it in water. Okay, so it would not be a strong base. It could be actually very close to neutral. It better be. You can drink it. You can't because you're not old enough, but okay, you can later, okay, when you're old enough, if you choose to. All right, making sense? These are all the kinds of things that could come up, okay, on that quiz on Friday. In addition to the stuff we are about to learn. All right, so we are going to go over solubility and the properties / weird behaviors of water. All right, a lot of this is probably going to be review. You learned terminology about solubility before. You probably already know what a precipitate is and homogeneous solution and a mechanical mixture and all that kind of stuff. Okay, if not, it'll be a refresher for you. Okay, so we have to learn the terminology related to solubility, solute, solvent, okay, that kind of stuff. We have to know what is meant by the term polar molecule. That has to do with why water is like the exception to every single rule that ever existed about chemistry. Okay, so we'll talk about that. Okay, and understand that because it is a polar molecule, water has many important and unique properties that make life on Earth possible. Okay, it just behaves differently. All right, questions so far? All right, so solubility was one of the physical properties that we used or that we tested for yesterday in the lab. Okay, solubility is based on, okay, whether something can, dissociate and thus dissolve easily, or if it's a molecular compound, just whether it's going to be soluble in water, okay, or soluble in something else. Solubility doesn't always have to mean does it dissolve in water. It can mean does it dissolve in something else. For example, if you get like oil-based stain on your hands because you were just painting your fence, okay, that doesn't come off with soap and water. Okay? But it does come off with paint thinner, Varsol. I wouldn't recommend gasoline, but it does come off with that, but you don't want to start on fire. Okay? So yeah, like anything that's like similar to it, it will dissolve in. So anything that's kind of oily or oil-based, it will come off with. Okay? Sometimes you can even, like if you have like even just butter or like canola oil or something like that, sometimes you can even get it to come off a little bit because they're more similar. Okay? Some things do dissolve in water, don't dissolve in it. Okay? That's all based on their solubility, which is a characteristic physical property. Okay? We can actually rate the solubility of things in how many moles per liter will dissolve. Okay, we're going to talk about moles at the end of the unit, but it's a unit of measurement that we use in chemistry. Okay, so if something is really soluble, it would be a high number of moles in a liter. Okay, if something was very low solubility, it would be a very small number of moles per liter. Okay. So a substance is said to be insoluble if it will not dissolve in another substance. So there's a definition. Insoluble means it will not dissolve in something else. Okay. If a substance appears during a reaction and settles to the bottom, okay? It's not soluble, okay? And we also can call it a precipitate, okay? A couple of the reactions that we do in our reactions lab, okay, actually produce precipitates. We'll take two clear solutions and mix them together and a solid will form. I don't mean like a block, I mean like a powder will form and fall out of the solution. It falls out of the solution, and when it's doing that, it almost looks like snow, okay? Snow is precipitation, okay? Precipitation is the process of falling out of something else. Snow, rain, hail fall out of a cloud, okay? Things that are not soluble fall out of solution, okay? They precipitate out, okay? Everyone kind of follow the definition there?
So precipitate is only something that like appears in a chemical reaction.
Yes, if you are just dissolving something in water and then it just starts to collect on the bottom, it's not really precipitating out, you've just saturated the solution and no more will go in. Okay, precipitates are generally what we see produced if a reaction makes a new compound that's not soluble, then it precipitates out. Yeah? All right, questions there on the terms? All right, more terminology. A solution, okay? A solution is any mixture that contains a solute dissolved in a solvent. It is also known as a homogeneous mixture. Okay? If something is homogenized, how many visible parts does it have? One. Okay? You see that term used all the time, especially with dairy products, peanut butter, okay, things like that. It all says it's homogenized because if you, I don't know how many of you have ever had this experience, but if you were like milk a cow, okay, and leave the milk, it separates. Okay, the cream rises to the top and everything else goes to the bottom. Okay, it's not homogenized. There's a process of pasteurization and things like that that cause milk to homogenize, that is to stay all one visible part. The same with peanut butter. Okay, if you buy most peanut butters, they are homogenized so that the oil stays inside the peanut butter. If you've ever bought, like I did a few weeks ago, by mistake, natural peanut butter, okay, I bought it at Costco. I was like, oh, that's a great price for peanut butter. It's a 2-pack, it's great. And yeah, natural peanut butter is a lot different than real, well, I call real peanut butter, okay, because the oil separates. Okay, all the chunky stuff, the peanut stuff, and all the salts and everything just goes to the bottom, and the oil will sit in a layer on top. And every time you want to use it, you have to stir it in, okay, because it's not homogenized. So if you hear something that is homogeneous or homogenized, it means it has been made so that it will stay with only one visible part. So if something is soluble, it will dissolve, and you won't be able to see it anymore. It will create a homogeneous solution or a homogeneous mixture. Okay, everyone follow the wording there? Okay, and then the other type is heterogeneous. Okay, so homogeneous means one, okay, the prefix homo means one, the prefix hetero means
More.
many. Yeah, it's many. Hetero means many. Okay, so heterogeneous mixture is going to have at more than one visible part. Okay, so if you put oil in water, it'll separate. Okay, the oil will sit on top, the water will go on the bottom. That is a heterogeneous mixture. Now, if I stir it up, will it very briefly kind of be all together? Yeah, that's mechanical. Okay, that's a mechanical mixture. I can force it together temporarily. Okay, but it'll easily separate itself, or could be easily separated. All right, if for whatever reason I put iron filings in sand, okay, or something like that, right, and mixed it together, it's not a homogeneous mixture. The iron filings and the sand are still separate, and if I stuck a bar magnet in there and went like this, I'd pull all the iron out. Okay, it'd be easily separated. It's a mechanical mixture. If you go to Subway, okay, and they ask if you want salt and pepper, they pull out one shaker. I've never understood that, but it does seem like it saves time. Okay, but that's a mechanical mixture. The salt and the pepper are all mixed together in that one shaker. Okay, you could easily separate them. Okay, you just pour water in there, and all the salt would dissolve, and all the pepper would float to the top. Okay, it's a mechanical mixture. I forced them together. Okay, but they haven't dissolved in one another. Okay, does everyone follow the difference? All right, so we have heterogeneous mixtures, more than one visible part, usually indicates low or no solubility, okay? And a homogeneous mixture, one visible part, usually indicates high solubility, okay? Are there any things we can do to change the solubility of something?
You could heat the solvent up.
Yes, you could. Okay? If you warm the solvent up, more of the solute will generally dissolve. Hot water dissolves more like sugar or salts or something like that than cold water does. Okay? What else?
You could stir it.
Yeah, okay. Agitation, okay, will cause it to be more soluble. Does that do what you say? Okay?
You could use a catalyst.
Okay, a catalyst usually makes a reaction happen faster, but it could improve the solubility a little bit. Okay, we often put like soap in water. Okay, soap helps water to remove things that wouldn't otherwise dissolve easily in water. The soap kind of helps with that, kind of a catalyst.
How about increase surface area?
You could increase the surface area. Agitation usually helps us do that, but yeah, you could put it over a wider area, okay, and that might improve it as well. Okay, all good ideas. All right. Making sense on those terms? Probably heard those terms before. Okay, and then solute and solvent, okay? A solute is the substance that is being dissolved. So if I'm making hot chocolate, okay, then I put the powder in the boiling water, okay, and the powder would be the solute, okay? If you put salt in water, the salt would be the solute. Anything that is going to dissolve is the solute. Does the solute have to be a solid?
No.
No. Okay? If you were, and again, you're not old enough to do this, but if you were to mix alcohol with something else, okay, the alcohol dissolves. The alcohol is the solute, and the water or whatever you dissolved it in is the solvent. Okay? So it's what gets dissolved that is determined to be the solute. Okay? It's more often than not the solid, okay, but it doesn't have to be the solid. Okay? All right, and then the solvent, that's the thing that is doing the dissolving. Water is termed the universal solvent. For some reason it doesn't dissolve everything, but that's what we call it. Okay? It dissolves lots of things. Okay? So it's the thing doing the dissolving. It's also why we often use that term when we're describing cleaning agents, okay, like Pine Sol or Mr. Clean or CLR or something like that. Those are solvents. They dissolve things that water doesn't dissolve very well, or maybe not at all. Okay, if you've got like the soap scum and the hard water scales and stuff building up on the inside of the shower, okay, you throw a little CLR at that, and it's a miracle, it's all gone. Okay, because CLR is a solvent that can dissolve some of the things that water does not dissolve easily. Okay, so a solvent is anything that will dissolve something else. Okay? All right, making sense? Probably review. Okay. Okay, and then the precipitate. Okay, so the definition of the precipitate, okay, any solid which is produced in a reaction and will not dissolve in solution. Okay, so it kind of looks like this. Okay, you would see it collecting at the bottom, and I do have a short video I'll show you of one forming here. But I'll give you a minute to write that definition down if you need it. All right, now, that comes to the idea that some things are soluble, some things are not, some things should be, and some things should not. Okay, so if I was to say to you, should a Twinkie be soluble in water? What would your answer be? A Twinkie is cake, right? I mean, it's got cream filling, but it's cake. And most cake, if you were to try and dissolve it in water, it doesn't dissolve, right? It might get soggy, but it doesn't dissolve. Well, the original Twinkie was not soluble in water because the original Twinkie was made of, well, real ingredients like eggs and milk and butter, okay, and cream and things like that. Okay? The problem with that is that it doesn't have a very long shelf life because things like eggs and milk and cream and flour and sugar, they can spoil quickly. So they didn't have a long shelf life, which means as a company, you're probably having a lot of your product spoil before it's purchased, and then your profit margins go down, okay? So during the Second World War, the process of making Twinkies changed because a lot of the ingredients weren't available. They were shipping them, to soldiers, and it was wartime and all that, so they changed some of the ingredients, and then after World War II, they continued changing the ingredients to try and increase the shelf life. The shelf life, incidentally, now of a Twinkie is like 2 years. Okay, it's like ridiculous. It's not even really food anymore. But it now, instead of having eggs and milk and stuff like that, it's like protein, albumin substitute, milk, modified milk ingredients, high fructose corn syrup, okay, things like that have changed the ingredients. Now, when you stop using eggs, what do you suppose happens to the color of the Twinkie? Yeah, it looks like drywall paste. Okay, it's like this gray color that's not very appetizing. And the idea of a Twinkie, everyone pictures this bright yellow thing. Okay, so once you took eggs out and used the albumin protein substitute, they don't look like a Twinkie anymore. So they add things like yellow dye number 5, which is actually a known carcinogen and is banned in like most European countries, but is obviously allowed in North America, but it's not very good for you. And then lots of other things have been replaced with just different kinds of ingredients that are now soluble in water. Okay, if you take a modern Twinkie and put it in water, it almost all dissolves.
Wow, that's gross.
Yeah, it's pretty gross. Okay, I mean,
Twinkie water.
now, yeah, if you break your jaw and you have your jaw wired shut, the good news is you can still have Twinkies. You just put them in a glass of water and stick a straw in there, and in a little bit you'll be able to drink your Twinkie. But yeah, I don't know. Okay, it's some things are supposed to be soluble in water, some things aren't. And I'm not going on like a you should eat organic kick because I'm like the worst person for like eating. Yeah, it's something to think about. Like we've really modified some of the things that we actually eat in order to make them last longer and things like that on the shelf. So the definition of solubility, which is where I was going with this, is the degree to which a substance will dissolve in another substance. And I said earlier we measure that in moles per liter. Okay. So how much solute can go into solution before the solvent becomes, and this is another important term, saturated. Okay? Once a solution is saturated, it will dissolve no more solutes. Okay? So if I was to make Kool-Aid, okay, I generally like to make it a saturated solution. Okay? I put the little Kool-Aid crystals in there, and I use actually warm water, and then I dump sugar in, okay? And then I put it in the fridge. And I know it's ready when it's cold and there's a layer of sugar on the bottom that cannot be dissolved, because then I know that the Kool-Aid is saturated, okay, and it's gonna be good and sweet, okay, at that point. I don't actually drink Kool-Aid anymore, but as a kid, that's what I did, okay? That's how I would make it. All right, so saturated means can't hold anymore, okay? All right, questions there? Everybody good with that?
Twinkie looks like a dysfunctional egg.
Yeah, kind of does. Well, and the yellow dye number 5 is one of the first things to dissolve, right? So it's already turning pale, like compared to the one that's not in the water, and the water is already starting to turn yellow. All right, on the back of your periodic table, if everyone can take their periodic table out, you will find this chart.
Right here.
All right, this is your solubility chart. It allows us to determine whether an ionic compound will be soluble in water at 20 degrees Celsius, okay, or not. So the way it works is like this, all right? We look for the non-metal, or the negatively charged part generally, except for ammonium there, okay? We look for that up here in the top row, okay? And then we try and match it up with the positively charged part of the ionic compound in one of the 2 rows below. Okay? If I find the positively charged or the metal, okay, in the first row, sorry, not the first row, the second row, then that's very soluble. So that thing would dissolve very easily. Right? If I find it in the third row or the bottom row, okay, that is what we would say, they say on the chart slightly soluble, we basically say not soluble. Okay, so this row soluble, this row not soluble. Right? So I'm going to show you how that works. Let's say I have this compound here. Let's go with all right, let's say I've got that compound, silver iodide. Okay, I want to determine whether it is soluble or not. So I go in the first row and I find iodine. It's right here. Okay, now it says that iodine is soluble with most things, which is like the least helpful thing you could possibly have in this chart. So if you see the word most, it means, hey, look in the other one. Okay, so I have to look down here and I see that it's not soluble when it's copper, and I see silver in that row. Okay, that means that compound is not soluble. If I was to put it in water, it would simply fall to the bottom. Okay, it would not dissolve in water. Okay, or very little of it would. All right, so that one there, that would be not soluble. If I had let's go with lithium nitrate. Okay, so I look to the top row, okay, I see nitrate right there. It says it's soluble with most things. Again, yay, thanks, that's helpful. Okay, but it's not soluble with these things that I've never seen before. Okay, so is that compound soluble? Yes. Yes. Basically all nitrates are soluble actually. Okay, so yeah, soluble with most things. Now, what does this mean when it says group 1 ions? Yes.
Anything in the first column of periodic table, so hydrogen, lithium, sodium, potassium,
Exactly.
etc.
Yeah. These are your group numbers up here, guys. Okay, we've been talking about those before. We say, you know, everything in group 18 is a noble gas, 17, everything's a -1. Okay, so if it's with something in group 1, it's soluble. So if you see that, and you will, okay, on that chart, it means it's soluble with anything in the first column. If it says group 1 and 2, then it's soluble with anything in the first two rows, or first two columns, sorry. Okay, it's just basically saving space by not writing out every single thing in group 1. Just say group 1, that's quicker and takes up less space. All right, everyone follow there? Okay, here's what I want you guys to do. Try these 8. I want you to write these ones down and then write beside them S for soluble, NS for not soluble. Okay, let's see how we do with that, and we'll go through them here in a minute. Okay, let's have a look at these ones here. So for number 1, calcium sulfate. So the process is I find the negatively charged part. Sulfate is right here. Okay, it says it's soluble with most things in the first row, which basically means check the second row, and I see calcium there in the second row. So this is not soluble, right? Okay, potassium hydroxide. All right, so I see hydroxide right here in the final column. Okay, it says it's soluble with group 1 ions. Soluble or not soluble? Soluble. Potassium is a group 1 ion. Okay, so that one is soluble. Okay, lead 2 chloride. So look for chlorine. Chlorine is right here. Okay, soluble with most things. Look down below. I see lead 2 plus down here. Soluble or not? Not soluble. Okay, tin 4 fluoride. Okay, so fluorine is right here in its own column. Soluble with most things. And I don't see tin in the lower row. So, soluble. All right, copper 2 sulfate. Okay, well, sulfate is right here, soluble with most things. I don't see copper in the second row. Soluble. Yep. Okay, number 6, potassium bromide. All right, here's bromine, soluble with most things. I don't see potassium down here, so soluble. Okay, silver fluoride. Fluoride again has its own column, soluble with most things, but I don't see silver down in here, so that would be soluble. All right, and then I have beryllium nitrate. All right, well, nitrate is right here, soluble with most things. Beryllium is definitely not there, so soluble. Okay, pretty straightforward. Okay, in the second, or in the last row, not soluble, middle row, soluble. Okay, that's all you really have to do with that. All right. Okay, I'm going to give you guys about a 5-minute break here, and then we are going to reconvene at 9:30, and we're going to start talking about the polar nature of water, so you can talk amongst yourselves. All right, so now we got to talk about water. Okay, what kind of molecule is water? Ionic or molecular?
Molecular.
Okay, it's molecular. But didn't I tell you that anything that starts with hydrogen is ionic? Pretty sure I did, right?
Yeah.
Okay? It's just special, yeah. Water. If there's an exception to a rule, water is usually that exception. Okay? Now the reason that water is not an ionic compound is because of the way oxygen and hydrogen share their electrons. Okay? They are not traded like they are in hydrogen sulfide. Okay? In hydrogen sulfide, the electrons are just traded. Sulfur and oxygen behave a bit differently because of something called their electronegativity. Okay? So this little number right here, okay, below the atomic number, okay, for sulfur, it's 2.6. For oxygen, it's 3.4. It's much higher for oxygen. One of the highest ones is fluorine at 4. Okay? Electronegativity describes how hard something holds on to electrons. Okay? And so the more they hold on to electrons, well, the harder they hold on to electrons, the more likely those electrons are to be near them, okay, at any given time. Okay? Oxygen has a high electronegativity. Okay? Oddly enough, for a metal, so does hydrogen. Okay? When you look at some of the other metals, they're all like 0.8, 0.9, right? They're right around 1 usually, okay, which is pretty low. Okay? But hydrogen is a bit higher, right? And for a metal. So when hydrogen and oxygen go together, the electrons are actually shared as opposed to traded. Okay? So water is a special molecule just because it's the one molecule that kind of does that starts with hydrogen. Okay? So what we end up having, okay, is a molecule that looks like this. Okay? We got the oxygen atom down here. It's got 8 protons and 8 electrons. We have the 2 hydrogen atoms at the top, so it kind of looks like Mickey Mouse. Okay? And so we got the hydrogen, we got the proton here, and this is hydrogen's electron here. Okay, we got hydrogen's proton here, hydrogen's electron here. So by pairing up with 2 hydrogen atoms, oxygen gets its outer shell of electrons filled, right? It has a charge of -2. It needs 2 electrons to fill its outer shell. By joining up with 2 hydrogen atoms, that happens. Okay? But hydrogen, in this case, is not just willing to go, here, have them. Okay? It's like, I'll share them. I see you got a couple. I need 1 to fill my outer shell and be happy. So how about we get along? Okay? And that's what happens. Okay? They both end up sharing electrons, but the sharing isn't equal. Okay? If the sharing was equal, we would have a pure covalent bond like you see in most molecular compounds. Okay? Meaning the electrons are shared pretty much equally. They spend just as much time with the metal as they do with the non-metal. Okay? Oxygen's not like that, and thus water is not like that. Okay? In a water molecule, the electrons are shared by oxygen more. Okay? So it's kind of like, that friend, you go out and you buy a pizza, okay? There's 8 slices, and you're going to share the pizza. Your friend eats 6 of the slices, okay? I mean, technically you shared the pizza, okay? But if you paid for half of it, you didn't share it very well, okay? He got more than you did, right? Well, that's the way oxygen and hydrogen go together when they're sharing their electrons. So what ends up happening is the electrons end up spending more time down here. And that exposes, at the top of the molecule, 2 protons. All right, so you've got this thing that looks like Mickey Mouse, okay? And you got these 2 protons sticking out the top of it. And what's the charge on a proton? Positive, okay? Now, you've got to remember here that the hydrogen has an electron, okay? But because oxygen holds onto electrons more tightly than hydrogen does, that electron spends way more time hanging out down here, okay, than it does around the hydrogen atom. So we end up getting negative charges at the bottom of the water molecule and positive charges at the top. Makes it look like it's a charged particle when it isn't. Now, what do you suppose happens if another water molecule comes close to that one?
It can act like they combine.
Yeah, they could attract each other, right?
Yeah.
Like if they're oriented the right way, okay? If the oxygen atom of another water molecule comes close to one of those hydrogen atoms, they'll be attracted to each other. In fact, so much so that the hydrogen's like, you know what, oxygen's not being very nice to me, okay? It's like got my electron all the time. It doesn't share it very well. I like you, okay? And it'll just bond to this other water molecule. Okay, it'll create what we call a hydrogen bond with that other water molecule. Now, these are weak bonds. They break easily, okay? But they also reform easily. It's like, yeah, oh, you're very nice. Oh, you're gone. Oh, here comes another one. It's just these things, they break and they reform, they break and they reform, okay? But you've seen these happen before, okay? You ever notice how sometimes you can fill a glass of water slightly higher than the top, right? And you get that meniscus, that surface tension. That's what's happening. Surface tension is produced by this hydrogen atom bonding to another water molecule's oxygen atom. Okay? That weak bond is enough to create surface tension that almost makes it look like it's not a liquid. Okay? It can hold a little bit of that extra volume over the top of a container. Okay? Or after a rainstorm, you see water like beating on the leaves of plants, or if you have like a well-waxed vehicle, right? The water will bead and it'll sit there and it'll like stick. Or on a really cold glass, okay? On a humid day, you get the water beating on the sides of the glass and it'll stick to the glass, right? It won't fall until it gets like so big that that hydrogen bond isn't strong enough to hold it there anymore, and then it'll slide down the glass. Okay? All of those behaviors are the result of hydrogen bonding. Okay? And that happens because oxygen holds the electrons more than hydrogen does. Okay? And it creates positive ends and negative ends to the water molecule. Okay? And then it can bond, hydrogen bond with other polar molecules.
Is it kind of like, would this be related to how like companies have made water resistant like clothing and stuff, or?
What they will usually do is coat it with something that repels water, so water just can't penetrate it. So there's various like chemicals that they can spray on the surface and things like that. Like wax does that, right? Like if you put just drops of water on a candle, they don't soak in, right? They just run off. Well, the same idea is true when you polish up a car. Okay, there's a thin layer of wax that forms on the surface, and water can't penetrate it, and that's what protects the paint.
Is water like neutrally charged, or is it like both negative and positive charged?
Overall, it's neutrally charged, but because of the way the electrons are shared, the top ends end up being positive because there's no electrons up there, and the bottom end ends up being negative because all the electrons are down there. Okay? So if I do the math, water's neutrally charged. But when we look at it and how it behaves, it acts like it's got charged ends, because it actually does. Right? Even though the numbers work out, oxygen's greedy and holds the electrons down at its end more often. Does that sort of make sense?
Yeah.
So both are true, is what I'm saying. Okay, does that sort of make sense? Okay, so we call this a polar covalent bond. Covalent bonds are shared electrons. Polar covalent bonds are not well shared electrons. Okay, they're still shared, but one person gets to share them more often than the other. Right? And that's what water does. Water's not the only polar molecule. There are other polar molecules, okay? But water is the one that obviously we see the most, okay? And it's this polar nature that makes water do weird things, okay? What's another weird thing that water does that most other things don't?
Turns into a solid when it gets cold.
Okay, well, actually, lots of things will turn into a solid, but what is
It floats
water?
to the top.
It floats to the top, okay? You ever freeze a plastic bottle of water? What happens to it?
Expands.
Yeah, bottom pops out, gets round, right? Instead of being flat on the bottom, it pops the bottom out, okay? If you like freeze a glass bottle, it'll break, okay? The water will expand enough, it'll break the glass. It's how rocks, it's how erosion happens. Water gets in the crack of a rock and freezes and it'll split a rock open, okay? Water does that because it's polar. When all things, water included, when they get colder, start to contract, right? But because water is polar, it gets to a certain point, and now the negative ends of those water molecules are getting too close to each other. What do?
Expand.
They repel. Water takes up the least amount of space at about 4 degrees Celsius. Okay? It'll contract as a liquid. It'll contract down, and its volume will be the least at about 4 degrees Celsius. And then those water molecules start to get too close together. And right before it freezes, they pop away from each other and form a crystalline solid, okay, ice. But it's less dense than its liquid counterpart, okay? Which is very rare. Most of the time when something turns into a solid or freezes, it's more dense than its liquid counterpart, okay? So if I had like liquid mercury and a chunk of like solid mercury, so liquid mercury at like minus 40, okay, and solid mercury about minus 43, okay, and I drop that solid mercury in, it wouldn't be like an ice cube, okay, it would go clunk down to the bottom, okay, whereas ice, you plop ice in there, it floats up to the top. Now, how important is that for life on Earth?
Very.
Very. If water as a solid was more dense than the liquid, lakes would freeze from the bottom up, and nothing would live over the winter because they would all freeze right to the bottom. Okay, but because water is less dense in its solid form, okay, as it begins to turn into a solid, it floats to the top and it freezes on the top. And because it's, well, the way ice is, it protects the liquid water underneath from the colder air temperatures above, and that can preserve an environment in which aquatic organisms can overwinter. Okay, the liquid doesn't freeze right to the bottom, or the lake doesn't freeze right to the bottom. Okay, making sense? Okay, weird but true, right? Like it's just one of those things that water does that's really important. Okay, lots of living organisms also depend on water being polar to survive because they use the surface tension of water. Okay, you ever seen like bugs landing on a lake or on a river, right? And they can just float right on the top. It's not because they're actually floating. What they're doing is they're not breaking the surface tension of the water. They're just sitting on the surface tension. Okay, you ever seen the Jesus lizard run across the water? Yeah, I can't remember what his real name is. Everyone just calls the nickname Jesus lizard. Okay, it's basically doing the same thing. It moves fast enough and distributes its weight enough that it doesn't break the surface tension of the water, and it can literally walk across the water. Okay, in a very awkward fashion. If it were to slow down or have to go too far, okay, it would fall in. Okay, but over short areas, yeah, it can walk across the water very quickly using the surface tension of the water. Okay, making sense? Okay, so sharing in a polar covalent bond, and that's what we have to remember, okay? This is a polar covalent bond, okay? Electrons are not shared equally. Okay, on a unit exam or a quiz, if I was asking you, okay, about water, okay, one of the things I would look for there would be the words polar covalent bond or polar molecule. And if you're a polar molecule, it is because electrons are not shared equally. That's what creates a polar covalent bond, and that would be part of your answer for sure. Okay, why is water different? It's a polar molecule, and it's a polar molecule because its electrons are not equally shared. Okay. Now, what does that lead to? Okay, that's what we also have to understand. It leads to water doing things that other molecules don't because it acts like it's charged. Okay, it's got two positive poles, okay, polar molecule, it's got two positive poles at the top and kind of two negative poles at the bottom, okay, as well, right? So one water molecule can actually hydrogen bond to 4 others. It has 4 points of attachment, okay? The 2 hydrogen atoms at the top and the 2 electrons at the bottom, okay, can serve as attachment points for other charged or polar molecules. So that is what this diagram here is kind of trying to show. Okay, so this one water molecule in the middle can hydrogen bond to the negative end of this one. It can hydrogen bond to the negative end of this one. Okay, it can hydrogen bond to the positive end of this one, and same with this one here. Okay, those charged ends get near the oppositely charged pole of another water molecule or another polar molecule. They'll form a hydrogen bond. Okay. Now again, hydrogen bonds are not strong. They break very easily, but they also reform very easily, okay? Because they're just based on, oh, there's another one over there. Oh, there's one over there, okay? If there's any number of charged particles around, break, go, okay? They just go anywhere.
Are there any other polar covalent bonds?
Yeah, ammonia, NH3 is a polar molecule. The only one I'm thinking of off the top of my head, but there are others, yeah. They're not as common as regular covalent bonds, but. Okay, another place where this is useful. If it wasn't for water being a polar molecule, plants would not be able to transport water from their roots to their leaves. Okay? Is this statement true or false? Plants use 0 energy to transport water against gravity from their roots to their leaves. True or false?
I'll take it there. True.
It's true. Plants require no energy. They don't expend any energy. There's no pump inside a plant that's actively pumping and using energy to push the water up the plant. What pulls water up a plant is when water evaporates out of the leaves, it leaves the minerals that were in it, the salts basically, behind. Okay? Water naturally wants to move towards those salts to balance concentrations in a process called osmosis. Okay? Well, if one water molecule moves towards that salt, that water molecule is probably hydrogen bonded to another one down below. So when it moves, it pulls the one below up. You ever play with the barrel of monkeys when you were a kid? Right? The plastic monkeys, and you could hook them all together and you can make a big long chain of monkeys. Okay? That's what water looks like inside the tubes of a plant called the xylem that transport water. Okay? They're hydrogen bonded to each other, and when one moves towards the salt, it pulls the ones below it. Okay? It requires no energy at all. It's just using the polar nature of water and osmosis. Okay? No energy required. Think about that. Think about like a giant sequoia that can be 100 to 200 meters tall. Okay? No energy required at all to move water vertically 1 to 200 meters. Okay? Just uses the polar nature of water. Okay? All right, so the water molecule, basically shaped like a right angle. Okay, so you got, like this and then like that. Okay, so you got, well, that's terrible the way I drew it, but it's a 90-degree angle. Okay, kind of like this. Okay, between the 2 hydrogen atoms. And that unequal sharing, like we said before, okay, can lead to the hydrogen bonds to other polar molecules. Okay, so if we're looking at what water does when it freezes, this is what happens. I was kind of explaining this before. At about 4 degrees Celsius, the water molecules are as close together as they can ever be. And when water freezes, they push apart. There's still those hydrogen bonds there that form that crystalline structure that we are familiar with ice. But that process is kind of random, which is why no two snowflakes, which is not entirely true, but it is effectively true. I mean, if you had a whole bunch of snowflakes all side by side that you could see, they would probably all look different. Okay, that process of crystallization is not like in an ionic compound. Okay, this is a molecular compound, and it's because of those polar bonds. Okay, and it just kind of randomly will go apart and form that crystalline structure.
So, does that, like, I'm confused then, so, well, I'm not confused, so snow,
Yep.
you know, like snowflakes and stuff. So is that water that has not hit 4 degrees yet, or?
Nope, snow is going to be below zero. It's crystallized, but it's tiny little droplets. So when it turns to a solid, it forms the crystalline shape of a snowflake.
But how come it, like, how come it becomes like a powder?
Well, I mean, some ionic compounds that are crystalline can look like a powder.
You know?
Yeah. So powdery snow basically has to do with, this is going to sound weird because snow is water, but like the moisture content of the snow, right? The colder it is, the more powdery it seems. Basically, the harder the crystals are, the colder it gets. So when we get that heavy, wet snow that's like right around 0 degrees, right? That stuff is mostly, it's not powdery, right? It's very wet. You get the minus 30 degrees Celsius snow, that's very powdery, right? When you start having to shovel a lot of it yourself, you'll learn to like the light stuff.
So when water freezes and the bonds are all made randomly,
Yep.
how is it that when you look at a snowflake, that both the sides look the same?
Okay, so what I meant by randomly was that each individual droplet can have a different shape to it. That's what I meant by randomly. It's symmetrical. Like when that crystal forms, that crystal will be symmetrical, right? But the next crystal over could be symmetrical and look different, is what I meant by random. Yeah. Okay. That's also, guys, why snow can be a good insulator. When snow falls and those, the big flakes fall down, when they fall and they fall on the ground, they can interlock together, and between the snowflakes will be space. That space would be filled with air, which can act just like fiberglass insulation in your walls. Okay, it traps air pockets, okay, and doesn't allow the air to move, and acts as a great insulator. If you build a quinzee, okay, has anyone ever built a quinzee? Okay, you just make a big pile of snow and then hollow it out and crawl inside. Okay, that's a quinzee. They can save your life on a cold winter night. Okay, you can just crawl inside, or you can get the temperature up like even above freezing, a couple of degrees. It'll start to drip on you. Yeah, water does weird things, right? You were asking about the other polar molecules here. So we got ammonia here. Okay, it's another polar. Right? Hi. You were asking about that other polar molecule, right? Okay, so that's it there. Okay, any polar molecules can hydrogen bond. Okay, they can do that. Okay, then the tree. Okay, so I wanted to show you kind of how this looks in a tree. So if you could actually visualize the little water molecules inside the xylem of a tree, what you would see is two different types of hydrogen bonding. Okay, you'd see hydrogen bonding between water molecules. We call that cohesion. Okay, and that's going to be an important term as well. Okay, so cohesion, okay, is due to hydrogen bonding, okay, between water molecules, okay, or between like water molecules. Then there's also adhesion. Okay, adhesion means water bonded to another polar molecule that's not water. Okay, so the water can stick to each other and the inside of the tube. Right? That's what keeps it from falling back down. Right? You guys ever notice this? If you have a really thin straw, it's super easy to pull water through it. But if you have a really thick straw, it's harder. Okay? In a thin straw, this process is strong enough to support the column of water inside the small straw. The bigger the straw gets, the more unsupported weight or water there is in the middle of the straw. Remember, these bonds are not very strong. Okay? They're very, very weak, in fact. So we can't have a column of water like this thick and hope that it'll be supported by hydrogen bonds. It won't. The tubes inside of a plant are microscopic. Okay? That's how a big giant sequoia can transport all that water. It's got millions and millions of tubes that are all really tiny, that are all filled with water, and they're small enough that that hydrogen bond is strong enough to support the water inside. Okay, so the two behaviors of water are cohesion. Okay, so cohesion is water to water. Okay, adhesion is water to any other polar molecule.
You said adhesion, sorry, was.
Is water to any other polar molecules on the next screen here, I think.
Oh,
Adhesion, right? So clinging of a substance to another, right? So it's water to something else. Okay, so that thing I was talking about with the tubes being really small, okay, if you want and you have the equipment, you can try this at home, okay? Just have a regular drinking straw, put it in some water, put your thumb over the top, pull it out, the water will stay inside. Okay, try that with like a piece of pipe. Okay, if you got like some plastic pipe, okay, put it in some water, put your hand over the top, create a seal, and see if it'll hold it in there. Okay, it won't. The hydrogen bonds are not strong enough to support a column of water like that would be in a pipe. Okay, so yeah, it won't work unless you get like an incredible suction, okay, somehow against the top of that tube, but it probably won't work. All right, so some examples of that surface tension. Okay, so what creates the surface tension in this water droplet is cohesion. What keeps the water droplet from running off is adhesion. Okay, so water to something else, adhesion, water to water, cohesion. Okay. All right, and apparently you can do this. I spent one afternoon trying.
I did it.
So you did it?
Yeah, I have a video on my laptop of me doing it.
Okay, we're gonna have to see that sometime.
Oh.
Because yeah, I tried it like for a whole afternoon. It's one afternoon of my life I'll never get back. Okay, because I couldn't make it work. And I tried. I bent the ends up so they wouldn't break the surface tension. It just didn't work.
You have to use dish soap though.
Oh, you have to cheat.
Yeah.
Oh, see, that's what I didn't do.
It doesn't work otherwise.
Okay, yeah, that would increase the surface tension. Okay, now that makes more sense. All right, and then, like we said, okay, at that interface there, okay, if you got something that's light enough, okay, like these water striders, okay, they can sit in the surface tension. They're not heavy enough to break. You can skip a rock. Skipping a rock is because of surface tension. Okay, you make that rock bounce off the surface. If the rock is flat and you get the flat side hitting the surface, it'll bounce. You throw a jagged rock, okay, and you might skip it once, okay, but it's probably not going to skip too many times because the jagged edges are going to break the surface tension. Okay? Similarly, you can't skip a rock by throwing it straight down with the water. Okay, it doesn't work that way.
I mean, if it hits the bottom.
Well, it hits the bottom, but that's different. That's not surface tension. That's bouncing off the bottom. Okay. All right. Questions on any of that stuff, guys? All right. Perfect. Good job today.